Chairman. I will present to you some results of research project on rolling counter fatigue of hardened steel for gear construction, especially regarding the propagation of subsurface cracks. The presentation will be composed of two parts: an experimental analysis and then some results numerical types. Subsurface crack nucleation and propagation is typical of rolling counter fatigue phenomenon in hard steel, and in particular way crack nucleation is favored by the presence of inclusions like oxides and sulfides, while subsequent propagation is it happens mainly by shear mode, mainly in mode 2 in this case, and is led by orthogonal shear stresses. The crack can go for a long way before branching towards the surface and causing severe and sometimes catastrophic damages like deep shelling or piece crashing or so on. So this is a phenomenon quite complex to be studied and very difficult to be reproduced in laboratory because crack propagated in mode 2 have the tendency of branching into mode 1, so it's very difficult to study this phenomenon, and for this reason very poor information is available in literature on this topic. Autopropagation is also strongly affected by crack face interference, which causes the so-called sliding mode or roughness mode closure effect, and this effect is able to increase very significantly the propagation threshold because of the locking effect between asperities of the crack faces. And we remember that crack propagation threshold is also affected by the shock crack effect, that is the dependence on crack length. The investigation was carried out on having specimens which was an object of a rolling counter fatigue test and crash campaign made on typical steel for gears production, and the test condition of the specimen were pure rolling, contact pressure of 2000 megapascal, and about 800,000 cycles. Afterwards, macro spanning phenomenon happened, which is reported as an example in this picture. After the test, the specimen was cut along its transversal section, looking for and examined by optical and electron microscope, in particular looking for subsurface cracks different to the minor one, so different to that causing the macro spanning, in order to study the damage evolution in an intermediate state. This, we found different subsurface cracks, and this is a significant one representative of the behavior also of the other cracks. We can note it's a quite long crack, about 3 millimeters, and examining it in detail, we can note some particularities. The first one is faceted fracture morphology, which is typical of shear propagation. especially near the crack tip. Another peculiarity is that the crack opens gradually from the tip to its central zone, and in the central zone the gap reaches a few microns. And another aspect is the presence of several microparticles entrapped between crack faces, which act as firm bodies in the wear phenomenon between the crack faces themselves. This is a picture showing more in detail the phenomenon of microparticles origin. We can note an incipient detachment of these particles from the crack faces, interfering during cycling contact, and also the typical wave aspect of the crack. And on the right, we can note the same phenomenon in a more advanced state, where the microparticles are almost completely detached from the surface of the crack. In some region, these microparticles were also further fragmented and appearing like a sort of gray band between the crack faces. It is interesting that this phenomenon was also observed by Matsunaga during a torsion test on bearing steel. The ring was finally broken after immersion in liquid nitrogen to observe its fracture surface, on which evident sliding and flaking phenomenon were observed, which are typical of sliding mode propagation. So, to summarize the experimental evidences, we can make some comments on the crack closure phenomenon and its evolution under cyclic shear stresses. We saw the microfailures of the contacting material layers and consequent formation of microparticles, which act as bodies in the wear phenomenon between crack faces, and sometimes are fragmented into a finer microstructure. As a consequence, we noted a progressive reduction of locking effect between crack faces, moving from the crack tip to its central zone, due to wear, which causes a reduction of asperity surface slope and increasing crack opening. Numerical investigation was carried out on the same component in order to better understand and describe the phenomenon of crack propagation, in particular the effect of crack faces interference. The model includes a subsurface crack under the action of a moving Earth pressure distribution, which simulates the cycling rolling contact action. Different finite element models were developed for the same. A first one is shown in this picture, is a uniform pattern crack front model, which means that the crack is modeled as with a faceted pattern with teeth having constant slope along the crack. The crack was modeled independently and then tied to the body with multi-point constraints condition. crack tip was modeled by quarter point technique, and the stress intensity factor was calculated by displacement field with the crack tip. Unilateral contact with friction between crack faces was assumed with a value of 0.25, and several analyses were carried out changing tip slope and crack length. Another model considers non-uniform pattern crack front, which means that the tip slope changes, in particular reduces, moving from the crack tip to the center of the crack, in order to reproduce what we noted experimentally. And we schematize for this aim the crack in the different regions having different tip slope. And finally, a third model was developed, which was a variation of the previous one, also including a central flat region, simulating the presence of inherent defect, an inclusion, which was modeled as a persistent crack according to the Murakami approach. In this picture is reported the results in terms of applied stress intensity factor, mode 2, for the constant slope models, which note a very significant effect of this parameter of the stress intensity factor, which means a very important locking effect. In this picture, we noted is reported the non-uniform model crack curve together with some curves referring to different tip slopes, and the curve referring to the persistent defect. We note that the non-uniform pattern crack front is overlapped to the curve referring to the slope of 30 degrees for short crack length, because this is the slope experimentally present near the crack tip. But also for longer crack, the curve remains quite low, which means that the closure effect is mainly due to the roughness near the crack tip. And concerning the curve referring to the crack emanating from near defect, we note that it starts from a higher value due to the presence of a flat crack, then it decreases rapidly, tending to the non-uniform pattern crack front. And so this curve presents a minimum, which means that if the applied stress intensity factor falls below the propagation threshold, a crack arrest is predicted by this law. But wear is supposed to act also on arrested crack by smoothing the asperities between the crack surface during the contact cycles, then increasing the stress intensity factor, and if this reaches the propagation threshold again, the crack is further allowed to propagate for a step, but after this step, new rough regions appear at the crack tip, so the stress intensity factor is again decreasing, and so on. So the crack is expected in the first stage of propagation to propagate, grow by a subsequent stop and go until it becomes large enough to propagate in a continuous way. So, coming to conclusion, we observed that mode 2 propagation of subsurface cracks is strongly influenced by sliding mode closure due to the roughness interference, where progressively reduce the locking edge level between asperity faces, passing from the tip to the central zone of the crack. Anyway, the effect of closure on applied stress intensity factors depends mainly on the roughness near the crack tip. And cracks emanating from mineral defects can arrest after a propagation step due to the locking effect of the roughness, but where can progressively reduce roughness allowing further propagation. So all these evidences can be very useful to interpret the results of tests for determining shear mode propagation threshold, which is a very complex topic.